we create join trees up to level 3 and level 4. The reason we choose join as the level indicator is that the joins are the most resource-consuming operators in queries. After join operators are constructed, other operators can be inserted. And after the query tree is fully inserted, we can translate them into query string. Following this approach, we covered queries that have various types of difficulties and that covers all the schemas and all the possibilities of the join and the single columns that could be asked. In order to use the massive amount of generated queries, we want to quantitatively model the queries such that we can analyze them in detail. The model must capture the cost of the queries very well. We rely on the optimizer in DBMSs to give a cost estimation first. We extract the statistics in the query plan, the execution plan, got from the server as a vector. As shown in this figure, the execution plan is got by using the command explain analyze format equals to 3. The operator with the most indentation is executed first, and level by level, it reaches the oldest operation. In this situation is the sort operator at the beginning. And there are 2 brackets after every operators that have non-negligible costs. In the first operator, the statistics of costs and rows are estimated from the optimizer with cost model built in the system. And in the second bracket is the actual running time of this operation and the number of rows in the result. So the result of extracting the operators will be shown in this figure. Operators with non-negligible costs are hash join, nested loop inner join, table scan, index lookup, single row index lookup, and filter. For each of the operator, we put the sum of costs, sum of rows, touch, and the number of this operator into the vector. For example, for the inner hash join operator in the query plan, there are 2 of them. So we put the total number of inner hash join as 2 in the operator. And the first one has estimated cost 263150, and the second one is 24311. We put the sum of them 287562 as the sum of cost in a vector. Similarly for the rows. However, with the estimation from the cost model, the statistics actually have a very large error. For example, here in the first bracket, the estimated number of rows of the result of this inner hash join operator is 147478. But the actual number of rows after executing this operator is actually only 243. So in the end, if 2 of the queries have the similar cost vector that is extracted from the query plan, they actually might correspond to quite different performance. You can see that these 2 vectors have almost the same statistic, but one of them only need 1.7 seconds and another of them need 10 plus seconds. So we have to enhance the accuracy of the cost model. And our approach is to use an operator level prediction. For sake of time, we'll save the discussion, but one intuition is that instead of using the statistics estimated by the cost model in the DBMS, we build a single operator predicting model using machine learning techniques, using gradient boosting tree regressor to estimate the cost and rows ourselves. And we mix the statistics we estimated with the statistics estimated from the DBMS. And in this way, we managed to achieve an acceptable performance error. So after generating and modeling enormous queries, we're going to cluster them. Our motivation is that if we can find the best configurations for all the generated queries, then we can respond to all types of queries very fast with optimized configurations. But it's not realistic to optimize all the queries separately. So we think if it's possible to only optimize queries that share similarity with others, and using this query as the representative query, we can recommend configurations for similar queries without actually optimizing them. So this is actually clustering. Therefore, we come with this idea to find representative queries and only tune them to give recommendations for other queries in the same cluster. The algorithm for query clustering we used in this project is dbScan. It's a density-based clustering algorithm. Given a set of points in a space, it groups together points that are closely packed together. It has two parameters. Epsilon is the maximum distance for two samples to be considered as neighbors. And the second one is the minimum number of points required to form a dense region, a cluster. So one example, one visualization will be like this. The points are closely packed together, are clustered, and are colored differently from others. So there are a total number of 3 clusters for these queries. In our query clustering context, imagining each of the point as one query, and we are going to put queries that are similar to each other in one cluster, and we select one representative queries from each cluster to represent all the similar queries, and we optimize targeting the one query to give suggestions for configurations for other queries. And this is how we selected the parameters for the algorithm. We'll save the discussion. And this is the result. This figure shows all the queries that are other than the representative query in this cluster run on the configuration that is recommended by optimizing the representative query alone. We can see that all queries are optimized. There's no conflicts as we've shown in previous session between the queries. So we have more than 100 clusters in our project. When user queries come in, we can compare them with existing representative queries and react with optimized configurations fast. And with all the clusters representative queries optimized, we can also predict failing queries. We construct this heat map, which describes the coefficient of correlation of performance change of all the representative queries from different clusters. That means it describes the relevant change of different representative query performance with the change of configuration parameters. If two queries have the coefficient of correlation close to 1, that means their performance change in the same direction with the change of configurations. Therefore, we can safely put them as similar, or the queries, their performance are changing in the same direction. There's no failing optimization for them. However, if two of the queries, for example, one is user query and one is the query for whose configuration parameters we're using as the optimal configuration, user query coming and their coefficient of correlation of performance is near -1. That means the user query is going to fail. It's going to give a worse performance than other configurations. Therefore, we can achieve the prediction of failing queries, thus respond with different configurations. So we can achieve robustness with this approach. We're going to overview of the architecture and workflow of our system, specifically how they work to optimize queries and how they respond to newly entered user queries. And we will compare our system with existing ones to bring out our advantages. The architecture of our system is shown in the figure, starting with users providing config files, which are the choices of parameters like the action variables and the status variables to be observed, and initial values of them. The system manipulator initiates the first round of running the workload. After running the workload, performance collector collects the performance matrix and database status and pass it through the optimizer. The optimizer then responds with the recommended configuration, and the recommended configuration is passed to the MySQL server by our system manipulator. After updating the configurations, the workload is executed again, and the performance database status is collected again and passed to the optimizer. By iteratively doing this, our optimizer finally learns what's the best configuration given the database status and performances. As for responding to user queries, with all representative queries we generated and optimized, we can respond to most type of user queries with optimal configurations by comparing its cost matrix vector to the existing representative queries cost matrix vector. And we give the suggestion for the most similar representative queries configurations as the best configuration. In practice, queries might come at a higher efficiency, and some of the configuration parameters need the system to restart again to become effective. Therefore, we cannot respond to each single query with different configurations. Our system's strategy to respond to user queries and tune the system happens when 1. Queries with correlation coefficient near -1 enter. This means those queries are going to have relatively bad performance on our current configurations. Then we analyze the query, we extract the cost matrix without requiring actually running them, and compare the matrix vector to our representative queries and suggest the best configuration. And the situation 2, when majority of recent queries don't fall into the cluster, which has the best performance on our current configurations. That means even the queries that are coming in don't have a very conflicting performance with the current cluster, but they might not have the best performance on top of our current configurations. Then we optimize with respect to the recent queries again to give a new set of configurations. And this makes our tuning more robust because we can predict the query without actually running them before they fail. And compared to existing approaches, our system can be adopted to different DBMSs with the approaches that we've described in previous sessions to generate clustering queries and analyze them automatically, as long as the scripts for extracting queries and operating the systems are provided. Second, our system automatically detects when the performance is not satisfying and tune the configurations itself without requiring users to submit tuning requests, which might be late already. And last and most importantly, our system demonstrates more robustness with the prediction of failing queries, because when failed query enters, we can automatically detect them and react with our best configuration. In the last session, we're going to analyze the limitations of our project and give some recommendations of future studies. First, the modeling of workload. There's not a unified way of modeling the workload. The difference between training workload and user queries always exists. If we model the workload to run the queries in sequential, the users might submit queries at the same time and run them concurrently. However, if we concurrently run the queries, user queries might come at a different pattern. It's not correct to expect two sets of workload to demonstrate exactly the same behavior. And secondly, collecting training data that is going to be used in reinforcement learning is a very low efficiency. Each round of interaction with the system needs to completely run all the queries in the workload, plus the time to manipulate the system to collect the performance, to ask the system start again. One iteration is not negligible already. Imagine run this iteration for thousands of times until the model is able to learn. And there are several future studies. First is that for our current system, we select the action variables and status variables manually. If studies can be adopted to automatically select the actions and status variable, then the system will become more automated. One interesting way of doing this will be using reinforcement learning or statistic methods to give an analysis of what's the status and the action variables that reflects our needs the most, and then construct the architecture of the neural network automatically. And this falls into the area of automated machine learning. The second recommended future study will be that in our current approach, our reinforcement learning don't consider the workload. We change the workload and we reassign another reinforcement learning task to our learner. If there's a unified model which can take the workload into consideration, then the whole system will be more general. With this, I end my presentation. Thanks for listening.